All right, today I'll be talking about materialized views, secondary indexes, and filtering. It's Scylla, but filtering didn't make it to the title because it's already too long. It's only 3 lines. These features have been experimental for a while, and now they're going GA. Finally, they're much mature enough. All right, that's me. I'm a Scylla developer since April 18, and I spent most of that time implementing materialized views, secondary indexes, and filtering. Let's move to my talk's agenda. First, a quick introduction on what actually the presentation title means. Then there are 3 major parts: materialized views, secondary indexes, filtering. And these features are all similar in a way. They can be alternative solutions. They can also cooperate with each other. And I'll be talking about use cases, implementation, and examples. And finally, there will be a summary, including our future plans, what we're going to optimize and how. So, finally here, what does it mean? Materialized views have been experimental since Scylla 2.0. Then came secondary indexes in 2.1, and filtering was actually not part of Scylla before. And let's skip to 3.0. Materialized views are going to go GA in 3.0, so do secondary indexes and filtering. And as you can see, it took a while for all these features to go from experimental to GA, but there is a reason. They are really complex in a distributed system. There's consistency issues, there's performance. And as you know, in Cassandra, there were actually retroactively marked experimental. So it says something about the complexity. Filtering wasn't that super complex because we just implemented it, but all in all, those 3 are going GA. They provide a complete solution for some of the problems. Part 1, materialized views. First of all, why do we need them? Let's see how the world looked like before materialized views. So with SQL, everyone knows that querying is done by primary keys. And when you design your data model, you should be aware of that. You should prepare it in such a way that you will be querying the primary keys. So obviously the internet is full of questions like, I've got this schema in production with certain primary keys, but I really need to query by something totally different. How can I do that? And it is possible. And let's see how it could be done. We have a super simple table. I wish the names of the columns were more human readable, but then it wouldn't fit nicely into the slides, so they're just letters. Let's assume we have such a table, and we want to query by regular column V, which is not allowed just like that. So imagine we have another table, table 2, which would store exactly the same data, but in a different orders, such as our primary key would be the column V. Then we could just query the second table and get the result we need. Same goes for another, like any other column. It can be a clustering column. If we want to query just by that, it would be really nice if we had a second table that has the exact partition key we need, so we can query it. So that's called manual denormalization. And it's generally a nice idea, but it brings several problems with it. First of all, it's manual, so it's the user's responsibility to keep track of all the consistency problems. Then, since there can be multiple tables we want to denormalize, we as a user would need to keep track of all of them. And then there's problems like what if one of the write fails, or we forget to update one of the denormalized tables that we have. And then our denormalized tables would go out of sync, so it will no longer be reliable to query from them, so all our effort would be wasted. And we really want to avoid all the problems. And let's see how complex a regular update could be with a denormalized table. Here we have a base table, which is, the indentation is really off for column C. We have a very simple table, which we created, and we also created a denormalized table to be able to query by the value of v. That's how it would internally look in the database. Nothing scary so far. It's just our base table has some data, and in the denormalized table we inserted exactly the same data, just in a different order. So let's try to update the value. In the base table, we just want to update the value of a regular column from 8 to 9. So we prepare a proper statement. But in the denormalized table, since v is our partition key, we need to first remove the row with partition key 8 and then insert another one with a new value. But the problem is, how do we know it is 8? Because on the left side statement, we didn't really state from what we need to update. And that's why, like, the only way we can get the value is by reading the base table first. That's the meaning of this slide title, read before write. And it's a costly operation because instead of just writing, we need to read first and then prepare an update. And it's not only a performance issue, but also it's a problem with consistency, because imagine that we read that the value is 8, but in the meantime, some other user also updates the value to 10. Then we fail to remove the 8 because it's no longer here. We just add another row, and we end up with the normalized table that is totally out of sync. So we have a big problem. Fortunately, Scylla comes to the rescue with all of these problems. Materialized views are a way to provide automatic denormalization to your tables. Automatic as opposed to manual means that everything is handled by Scylla, and you don't need to worry about, first of all, generating all the view updates on your own, because Scylla does that for you. This read before write problem is also applied when necessary, and there's no consistency problem anymore because Scylla will just log the row, so it cannot be updated in the middle of our operation, and everything's fine. And also, since Scylla would manage all the materialized views, it will also expose useful statistics you can read. You can also use them to see if your design was right, or maybe you should change your data model if the statistics say that something might be off. Let's see an example. Here's how to create a materialized view in CQL. This is the one to the right. You can see it's kind of similar to a select statement. And that makes sense because you can think of materialized view as a result of a select statement that's stored in the database for faster reads. Below you can see how the internal representation would look like. It's basically the same as on the manual normalization slide. The values are here, like before, just in a different order, so you can query by whatever you want. All right, so materialized views can be created over a regular table, and its keys can be pretty much whatever you want, but there are some restrictions. First of all, if you want to use a regular column, you would be limited to one regular column to be in a primary key of a materialized view. Then the important part is that you need to include all base primary key columns in the view's primary key. There's room for being creative. You can use base clustering keys as views partition keys and so on, but all the columns must be there. And also, as you could see on previous slide, V here is restricted with not null because it acts as a partition key. So you need to provide all this where something is not null restrictions. Also, there can be multiple materialized views for every single table. Materialized views are identified by their name, and that's how you query them. Let's see some more complex examples. Here we have a table with slightly more complicated schema. We have partition key, clustering key, and several values. And we want to create a materialized view that what we want to query is just what value of clustering column C is connected to our partition key P. So that's all we select from in this statement. And you can also see that what we actually store in a materialized view is only what's necessary. We don't store all the values that were there in the base table because they can be big. We just store what we need. Another example, you can see that this is not null thing gets kind of irritating if you have really many columns to restrict. But here we have yet another more complicated schema. We have compound partition key, compound clustering key, and some values. And in the materialized view, what we were interested in was having part of the clustering key C2 and one of the values, but nonetheless we needed to add all the clustering key columns from the base to the materialized views key, because that's the restriction. We always need to include the whole base primary key in here. All right. Now that we know that materialized views are useful and cool, there are also challenges to overcome, and we overcame them all. First of all, consistency. If we create a materialized views, we expect all the data in this view to be synchronized with what's in the base table. We don't want some ghost rows to appear or we don't want some missing rows. We also need to be resilient to node failures. If in the middle of the operation one of the node fails or restarts, we don't want to lose some of the updates to not get inconsistent. Then another thing is that generating view updates can really stretch the throughput of our cluster, because especially if there are multiple materialized views in our cluster connected to one table, even a single modification, even a single write can spawn dozens of materialized view updates. And if we didn't throttle them at all, then it would be easy for them to overload the whole cluster. Not to mention streaming, which is something I will explain a little bit later, but in short, streaming can also be the source of generating very many materialized view updates in the short term. And finally, since we allow the materialized views to be created on tables with existing data, we also need a mechanism to fill these new views with data that already exists. So that's called view building, and that's another thing we needed to provide. All right, consistency, our challenge number one. Let me first explain the graph here. Blue circles are nodes. C stands for coordinator, B is base, and V1, V2 are view replicas. And this picture shows a flow of requests in time. So at first, coordinator sends a write request to the base replica, which then generates, after acknowledging the write, it generates the view updates, one delete operation and one write operation. Then after the view replicas finish, it's reported back to the base replica, and base reports back to coordinator. So it looks simple and easy, but there are two major problems with that synchronous model. First of all, its performance, because the client needs to wait for all of the replicas to acknowledge the write, and only after that the client could proceed with other writes. So that's significantly more than just a regular writing process. And secondly, the other problem is availability, because then if one of the, in this model, if one of the view replica writes failed, then it would mean that the base write is going to fail. So especially if you have multiple materialized views, that would mean that base replica availability would depend on availability of all these view replica nodes that are there, which is not good. We don't want that. And that's why synchronous model is not what we applied. Now let's see what changed. The first part is the same. Coordinator sends a write request, but then the base replica writes exactly in the same time that it took to generate all the view updates. It acknowledges back to the coordinator and says that everything is fine. The base write succeeded, and the view updates continue in the background. So we're done with the performance issue, because now we can return to the client faster. But as for availability, let's see what happens if the write fails. If it fails here, between coordinator and base, then we're safe, because it's basically exactly the same as the base write that would fail, and it happens sometimes. No view replicas were replicated yet. There are no ghost rows appearing anywhere. Everything is fine. But how about now? The coordinator received an acknowledgement from base replica that the write was successful, but at the same time, one of the view replica failed to get an update. Now we can just ignore that, because we would lose a view update, so we would go out of sync. And also, there's no way to go back to the coordinator and says, hey, actually one of the view replica writes failed, because it's in the background. The coordinator is already busy with something else. And finally, we don't really want the coordinator to know that something is wrong, because we already acknowledged that the base write succeeded. So what we do is hinted handoff. Hinted handoff is a general mechanism that has been in Cassandra for a while already. Basically, it's used for user writes when it's not possible to send something to the replica. It can be stored locally for a while, and when the replica comes back up, we can just resend it. So we can use that for user writes. So we thought, well, why not use that for view updates as well? So if, as you can see on this previous slide, one of the view replicas failed, one of the view replica write failed, we can just store this view update for a while locally on disk, and when the view replica comes back, the view updates will be resent, and that way we don't ever lose a view update, and we don't go out of sync. View building. As I told you before, when we create views on a table with existing data, we need to rebuild. We need to build the index data as well. We need to fill it with what's already here. We can't just do it synchronously, because there could be gigabytes of data to be processed, to be rewritten into the view. So the process is incremental. We do it token by token, and even if case of node restarts, we're safe because we'll just start the process over from the last checkpoint. We store the progress of this view building in system tables, which are readable for users, so we can check which of your views are in progress and which are complete. And it's worth noting that when the view is being built, you can read from it, but the results won't be full yet because it's in the middle of building, so it's not fully synchronized with what's in the base table. Backpressure. All right. Since generating view updates is a process that can really affect throughput of the whole cluster, we need a way of limiting it so it doesn't overload. You can think of it like that. If a table has, let's say, 5 materialized views, and you just want to update one row, you can end up with 10 synchronously sent materialized view updates. So this number can grow really fast, and we want to throttle that. So we did it like that. Base replicas have internal queues where they have their view updates they generated, and as the queues go full, that means the load is high. So this high load is reported back to the coordinator, which is allowed to decide that since the load is high on base replicas, some of the new writes will be delayed. And as the new writes are delayed, the queues are getting less full because less requests per second are coming out to them. So things stabilize. There was a presentation about the topic by Nadav. I hope you attended. And there's also a public design document for people really interested in deep details. All right, streaming. Another thing to consider when worrying about materialized views. Streaming is a mechanism used to transfer data from one node to another. It's used under the hood for operations like bootstrapping, repairing, rebuilding, and so on. You can think of it as moving SS tables from one node to another without all the proxies like mem tables and commit log. And it all sounds great, but sometimes we need to generate view updates after we receive such tables. First natural operation that needs that is repair, because since we're repairing the data, we want to generate correct view updates too. But even if we don't repair but rebuild or bootstrap, and the view building process of some views is not complete yet, we also need to generate view updates for that table to be consistent. We did it our algorithm is based on keeping these SS tables in a separate directory, and once all the views updates are generated from the SS table, it can be moved to a regular directory, and in case of failure, we can just scan the directory and restart the process of generating view updates from it. So again, we don't lose any view updates. Secondary indexes. We go to the second main feature, but we're not done with materialized views yet at all, because these two are interleaved. So again, what do we use secondary indexes for? If you wanted to search by a column that's not a key, we could, well, do a full table scan and then filter what we need client side, but first of all, it's a performance killer, and secondly, sometimes it's not even possible because it wouldn't fit in RAM. We could redesign our schema, do some manual normalization, or we can use materialized views. So there was a design decision to take when implementing secondary indexes. Our goal was to provide a way to index the column so it can be queried. And these alternatives are global and local indexing. And here are pros and cons. Global indexing can be, like, the implementation can be based on materialized views. And that makes reading and writing scalable because it's a distributed operation. Local indexes, on the other hand, local indexing means that we keep a local structure for every partition that stores our data. So writing to it is really fast because we just update a local structure, but reading is not scalable at all because we need to contact all the nodes. One more topic, cardinality. Low cardinality means that there are few unique values in our column. And in case of global indexing, low cardinality implies a problem, which is wide partitions. And on the other hand, high cardinality, so many unique values, are not a problem at all. For local indexes, however, low cardinality also causes local wide partitions, but they are local, so it's slightly better, still not very good. But high cardinality means that we have a performance issue because we contact huge data structures that just to return a few rows. So bottom line, we decided to go with global secondary indexing. Here's an example how you would create a secondary index. You can see it's way more human readable than creating a materialized views. It's very straightforward. I even managed to fit 2 examples in half of a slide, so it's really good. So we have a regular base table like before, and if you want to create an index on it, we just literally create index on this table with such and such column. And internally, it looks almost like regular denormalization. We also have a token field used for ensuring proper order, but that's more of an implementation detail. And as opposed to materialized views, we don't query secondary indexes directly. We just query the base table. And if an index can be used to fetch results, it will be. But this transparency, this ease of use comes at a price. Secondary index query is actually a compound thing, and it's a lie. It's not a query, it's 2 queries inside of one. So first we need to, when the query arrives, we need to contact our underlying materialized view to get all the base primary keys. And then after we have that, we can use these base primary keys to actually select our data from the base replica. More detail in a more detailed plan. First, we receive a query from the user. We then check if it needs indexing. If it doesn't, then it's a regular statement, so we just proceed. If it does, we check if the index exists. If it doesn't, then it's an error, so we return it. If the index does exist, we execute the first query, which extracts all the base primary keys. And then, since we have base primary keys, we can query from the base replica, and the results of this second query are returned to the client. Now there are also some problems with to consider with secondary indexing. And these problems are connected to paging. So, a quick introduction. Rows in the materialized view that keeps all the base table keys. These rows are small because they only store keys, and keys have a size limit. It's 64 kilobytes, but they are usually way smaller anyway. So for a default page size of 100 that's in SQL shell, usually we will not hit the internal limit, and we will just return 100 rows because they are all small. Base rows, on the other hand, can be much bigger. First of all, we can have some blob values in there that reach megabytes. We can have big collections in here. So even a single base table row can be big enough to hit the query size limit, and 100 of them is, well, even more likely to hit it. So we need to take that into account. And again, let me explain the graph first. C is coordinator, I is an index replica, and B is base replica here. And this one is the optimistic example. First, a coordinator asks for 100 rows. The index replica returns 100 keys. These are small, so they all fit. Then, using these 100 keys, we want to extract 100 rows from the base replica, and they were also small enough to fit, so they were all returned. Now, let's see the less optimistic example. The first part is the same. Coordinator asked for 100 rows. The index replica returned 100 keys. But then it turned out that base replica has really big rows, and only 3 of them were enough to hit the size limit, so we just returned 3, along with a special flag that says that our read is not complete yet. We still have rows left, but that would need to be handled later because we hit the limit. And fortunately, we can transform this information to the paging state that we return back to the client, so it will know where to start the next querying. All right, so we've got materialized views and secondary indexes pretty much covered. So which one to use? If you have a use case, which are better? Secondary indexes look more friendly. They're easier to create, easier to manage, delete, things like that. And they are transparent, so you just query the base table, and if there is an index on it, it will help you retrieve the data you want. It's helpful if you have some external libraries with hard-coded statements or whatnot. Also, secondary indexes do not actually denormalize data. They do not duplicate data. They just store the keys, which are small. So if we have tables with big wide rows with like 10 megabyte blobs or huge collections, we might want to use secondary indexes as opposed to materialized views, which would duplicate all the data. Materialized views have one big advantage though, latency. Since materialized view is pretty much a table when it comes to reading it, we just do one query. We don't do the 2 steps like secondary indexes, so we get our results faster. And also, materialized views are kind of a Swiss Army knife that you can create complex schemas with them, create some complex primary keys if you want, while in secondary indexes you can just mark one column as being readable. Yeah. So we can query by it. All right, filtering, the feature that is also connected to materialized views and secondary indexes in a way. All right, so everyone who ever tried to query by something different than primary key probably saw that message. And it states that generally you shouldn't do that. You shouldn't restrict something else than a primary key. But if you really want to do that and you're aware of the potential performance problems that it may cause, you can just type in allow filtering so we know that you agreed to that the performance can be bad. So, which queries may need filtering? You can see that these bullet points are kind of similar to those from materialized views and filtering. If you want to query for non-key fields or just parts of the key, then you can also allow filtering. But it's a little bit more flexible. You can also have inequality relations for primary keys or some other combinations that use some more complex restrictions. Then filtering might be the way to go. All right. Our implementation has a very fancy name of coordinator side filtering. And it means that coordinator first retrieves data from all the nodes as if the restrictions didn't exist at all. Then filtering is applied, so all the rows are checked if they match the restrictions, and if not, they are dropped. And after that filtering, only matching rows are returned to the client. And there's nice room for optimizations here, because we could potentially send some of the restrictions down to the replicas so they could pre-filter our results, so coordinator has less work and we send less rows over the network. So we can do that, but the base implementation just assumes that coordinator will do all the dirty work and filter everything. All right, one more topic connected to filtering is query selectivity. Low selectivity means that our restrictions are loose, so we allow almost all of the rows to pass our restrictions. And conversely, high selectivity means that our restrictions are very strict and we will just pass a few rows. Most of them will be dropped. So which one is a better candidate for filtering? Low selectivity queries are a clear winner here. And this is because filtering, as I told you before, works in a way that we first scan everything anyway and then drop the rows that don't match. So if we want to return almost everything anyway, it's really fine to scan everything. And on the other hand, if our queries are really selective and we would like to return just a few rows, like one, it's probably not a good idea to fetch 10 million rows first and then filter just one of them, because that's a huge waste of resources. All right. What are the alternatives for filtering? First of all, materialized views in some cases, also secondary indexes you could use, and their alternatives, so schema redesigns and what was there, and client-side filtering, whatever. All right, but filtering and indexes are not only alternatives, they also cooperate together very well. And here are some examples how we can combine filtering with indexes. Again, we have a rather simple table, and we create an index on one of the clustering columns. Now we want to query for rows that have restrictions on this column, but also some regular columns. So this query is valid, it will work, but how it will work exactly is as follows. First of all, we would use the index and fetch everything that matches our clustering key restriction. And only after that, on the rest of the results, we apply the rest of the restrictions. So we check if the value restrictions match or not, and if not, we drop the rows and we return what's left to the client. That way, filtering doesn't hurt that bad, because you can see that we didn't scan the whole table first. We just need to filter what's left, what's returned from the index. So if the index was very selective, let's say it returned 10 rows, it's not a performance issue at all to filter these 10 rows out and check if they match some additional restrictions. All right, what if we have multiple indexing, which is perfectly legal? Right now I added another index on V1, one of the regular columns. The rest of the example is exactly the same. So what would happen is also exactly the same as the previous slide. Since we can only use one index for an index query, we would use the index on the clustering column and then filter all the rows that match the restrictions. Right now, our super simple heuristics is to pick the first index that we find. That's why we went with C2. But there's room for improvement here with statistics, and I'll talk about it on one of the next slides. Okay. Now let's see yet another example. How filtering could work with some partition key restrictions. Now, aside from some clustering and regular column restrictions, we also have one partition key restriction. And how filtering would work in this example is that first we would extract only rows that are from partition with P0, and not only that, also sliced by C1, because we can't do that. It's a primary key prefix. So we can use that information to only fetch part of the table that will match, and then we will just filter the rest of the restrictions that are still here. But it's even better than that, because we can apply these key prefix optimizations also combined with indexes. So right now we have clustering, we have primary key restrictions again, and we have also one restriction connected to an index. And now usually what we would do is first query an index and then filter all the rows that this index returned. But in this case, we can do a very nice thing because there's actually nothing to be filtered. That is because we can incorporate our prefix restrictions into the index query, into the first query. So it already fetches only the base primary key that match all the restrictions, and then no filtering is needed because all restrictions were covered already. And with this kind of query, we don't even need to type allow filtering, because there's no filtering, there's no performance unpredictability. Everything's fine. And now a slide from the future, selectivity statistics. Imagine that we could have a good guess how selective our queries would be with every index. So if we had that, first of all, we could take a look at the statistics and see if they are the right, if let's say indexes are the right use case for for our case, because if our indexes tend to, if querying our index tend to return 90% of all rows, maybe filtering is a better idea. It will be, because filtering would just scan the whole table sequentially and then just drop some of the rows, while indexing would involve many random lookups, and additionally creating an index also takes up some space. It's not big, but it's still some space. But what's even better, we could use these statistics for multiple index queries. If we have a query with several restrictions and there are more than one indexes that that could be used, it would be the best idea to use the index with highest selectivity. So the one that would return as few rows as possible, because then the rest of the restrictions would be degraded to filtering. We would need to filter them. So yeah, right now we just pick the first index that we find and hope it's selective enough, but if we had these statistics, it would be really next level optimizations. All right, we've reached conclusions. So these three, materialized views, secondary indexes, and filtering, are going GA as of 3.0. They've been experimental for a while, and our users and open source community helped us by reporting tons of issues and bugs on GitHub, and we fixed them. So thanks a lot for that for that feedback. It was priceless and helped us a lot with reaching the state that we have now. Now finally some future plans. What we still want to do regarding the topic of views, indexes, and filtering. First of all, materialized view repair is something we would like to implement. It's just like regular repair. We would like to have the possibility to repair data between base replica and view replica. Then optimized multi-index support. That's what I was talking about two slides before. Selectivity statistics. If we had that, we could apply several optimizations to our index queries, and using indexes would be an even better idea performance-wise. Also, replica side filtering. We would really like to help the coordinator with all the filtering by pushing some of the work to replicas, because first of all, that would mean less rows being sent back, so less throughput wasted. And secondly, coordinator is already busy with other stuff, so it would be great if replicas would do some pre-filtering stuff for him. And as always, there are endless optimizations that we would like to apply that they would also never fit into that slide. So yeah, we'll definitely keep working on it.